Assalamu alaikum students, this is Talha Akram, and in today's lecture we'll discuss the half-wave rectification which is an expansion in the diode analysis and will include the time varying functions such as the sinusoidal waveform or the square waveform. In the previous lecture we have discussed the series and the parallel combination of a diode. So the process of removing one half of the input signal to establish a DC level is called a half-wave rectification. Let me bring the pointer here. Okay. So considering this function, which is a time varying sinusoidal function, in which we have two lobes, the upper lobe or the upper half, which is a positive VM, whereas the second lobe or the second half or the negative half is here this one, and this is the positive half. The positive half has a positive magnitude V of m, and whereas the negative half is a negative magnitude minus V of m. So and the sinusoidal signal is having the time period of t. The first half is 0 to t by 2, and the second half time period is t by 2 to t. So the average value of this sine signal is 0. So average value is what is the average value? Average value is the algebraic sum of the area above and below the axis. So this is the axis, and the average sum is the summation of all the values in this half and summation of all the values in this half. This is positive half, this is negative half. So for a perfect sinusoidal signal, the average value must be equal to 0. So considering this circuit, which is having one diode, this is an ideal diode, and a resistor is attached from where we are getting the output voltage, which is V of naught. So what we'll need to do, we'll generate a waveform V naught that will have an average DC value of a particle used in the AC to DC conversion process. So during the interval we have t is equal to 0 to time period t by 2. So diode will be in the on state. So this is a positive cycle, this is positive, this is negative, as we are using the conventional flow of a current. So in the positive half the diode will be in the on state, whereas in the negative half it will be in the off state. So positive half cycle make the diode forward biased. This is a positive half cycle, whereas the negative half cycle, let me find the razor. Okay. Whereas in the negative half cycle the signs will be like this and this, and the flow will be like this. In the negative half cycle diode will be in the reverse condition, so circuit will be open and we'll be getting a 0 potential at the output value V naught. Okay. This is an example that in the positive half cycle the current will flow in this direction and diode will be behaving like a short circuit. So what the input is, we'll be getting the same input as an output, which is V of m. So this is the ideal diode, so the drop will be equal to 0. So as soon as the input started, the output will also, signal will also get started. So in the positive half cycle we'll be getting upper lobe or positive lobe which is having a magnitude V of m, and in the negative half the current will flow in this direction. It will be, the circuit will be in this form. This is open circuit, so current will not flow, and here is the output t by 2 to t. We'll having a negative cycle. In the negative cycle the voltage V naught is equal to 0 volts, and this is the non-conducting region. Definitely from t by 2 to t we are having the non-conducting region. So as I mentioned earlier, that the average value is the summation of all the algebraic sum of all the values under this curve and algebraic sum of all the values under this curve. So average value will be the addition of this one and this one. This is a positive lobe, this is a negative lobe. So positive value algebraic sum of this region and the algebraic sum of this negative region will add both, and we'll getting the VDC value equal to 0 volt. But the case is quite different here. This is the output, basically this is the output. So we are getting the VM, the positive half, whereas we are getting the lower half equal to 0 due to this region, this one, and due to this cycle from T/2 to T. So the final output of a single sinusoidal cycle is this one, from here to here with the time period T. So the average DC value is 0.318 Vm. I'll share you a derivation in which I have proven that V of DC is equal to 0.318 Vm. So for the half cycle or half wave rectification signal, V of DC value is 0.318 Vm, because the lower algebraic sum of lower lobe is equal to 0, like this one, and the algebraic sum of the positive lobe is this one. Will getting the some value, and this and that calculated value is 0.318 of the total magnitude, which is V of m. So here is the derivation. Let us consider we have a sinusoidal signal having a having some time period omega t. So Vi is equal to Vm sine of omega t. This is the signal. So what we need to do, we need to find out the area under the curve. For the area under the curve, we need to take the integral. So V of DC is equal to 1 over t. T is the time period and the total interval is 0 to t, Vm or Vi dt. As 0 to t is divided into two halves, one is 0 to t/2, 0 to t/2, this one, and the second one is t/2 to t. So our final so the equation will be is equal to 1 over t Vm 0 to t sine of omega t dt. We divide this region into two halves, 0 to t/2 and t/2 to t. So here is the relation: 1 by t Vm, this will come here and the bracket started here, 0 to t/t sine of omega t dt plus t/2 to t sine of omega t dt. As you know, from t/2 to t the area under the curve is 0. So what we have done, we have put the value 0 here. So V of DC is equal to V of DC is equal to 1 by t Vm minus cos of omega t to 0 to t/2. So as we know, the time period t is equal to 2 pi, single pi and the 2 pi. So t is equal to 2 pi, we just need to insert this value here somewhere. So here 1 by t Vm minus cos of pi, we need to open it, cos of pi, because we need to put 2 pi here. T is equal to 2 pi, 2 is cancelled with 2, so it the only pi is left here. So minus cos of pi minus cos of 0, as we already knew that the cos of 0 is 1 and the cos of cos of pi is minus 1. So minus into minus 1, this will be minus 2 and this will be positive 2. So we need to cancel here. T is equal to 2 pi, so 2 will be cancelled like this. The answer will be Vm by pi, means Vm into 1 by pi, and 1 by pi is 0.318 Vm. So from this derivation it is clear that the average DC value of this truncated signal is 0.318. In case of negative half cycle, let the positive half cycle is 0 here and the negative half cycle is like this. So in this case the average value will be minus 0.318 for the negative half cycle. Okay, now replacing the original ideal diode with the standard diode, which is silicon diode. So Vk is equal to 0.7 volts. So the diode, we can replace the original silicon diode with the drop of 0.7 volts. This is what we have discussed in the last 2 lectures. So the applied signal must be at least 0.7 volt. If Vm is equal to 0.6, let it is 0.6, then diode will never be in the on state, both for the positive half cycle and for the negative half cycle. So the output will be like this. This is T by 2, this is T, this is equal to, let me change the color. Okay, let me take it black. Okay, this is the output of this signal if Vm is equal to 0.6 volt, because diode will never be in its on state. Okay, coming to original signal here, eraser. Okay, let me remove this one as well. Okay, so coming to the signal, let us consider we have a silicon diode here having the value of 0.7 or the threshold value of 0.7. So for the half wave rectification, what we need to do, let that here the diode is let 0.2 volt or 0.3 volts, and the drop is 0.7. So we're getting a zero signal here because diode will never be in the on state. So the output value is 0 somewhere here. Similarly, when the input voltage is 0.6 and we'll getting diode is in the off state, and we'll be getting a value of 0. But when the diode is input signal is 0.7, diode will be dropping 0.7 volt, the output signal is 0.7, and this is the threshold value at this point. Let me change the color. This is the point from where the signal will be increasing, the value of the voltage will be increasing. So at 0.8 volts, let 0.8 volts minus 0.7, the output will be 0.1 somewhere here. So it will be increasing like this, and the upper lobe final magnitude value is Vm minus Vk, where Vk is the threshold voltage for a diode. So if for the input signal Vm is equal to 10 volts, then it clearly shows for the positive half cycle it will be 9.3 volts, because the drop is 0.7 volt here. Okay, for the negative half cycle, diode will be in the off state and we'll be getting a zero signal. And what is this zero value shows here? When the signal is going down to 0, it will reach 0.7 volts, the output value will be 0. Then when it will reach 0.6 volts, then again diode will be closed and we'll be getting the zero value here somewhere, this place. Okay, this is the reason we have a small patch of 0 values, same like this patch, this is also 0 for a input for the positive half or the upper lobe. So the effect of VK on half wave rectification signal is shown here, that we'll be getting two patches of 0 values here. So the average DC value will be V0 is equal to Vi minus Vk, and the average DC value is 0.318, which we have calculated here. This is the value, but we need to replace the Vm with Vm minus K equation. So V of DC is approximately equal to 0.318 Vm minus Vk. If it's the lower lobe, then it will be minus 0.318, and if it will be a complete signal, then it will be straight away 0. Okay, coming to an example 2.16, in which we need to sketch the output voltage V0 and determine the DC level of the output for the given network in the figure 2.49. So the Vm is given here is equal to 20 volts. It means this is minus 20 volts, and it's a sinusoidal signal, and the diode is in the reverse state. So for the positive half cycle, let me see if there is a signal or not. Okay, for a positive half cycle, this is a positive half cycle. Diode will be in the off state, like it will be open here, and there is no, it will be disconnected from here. So the for this one, the output will be like this. This is equal to T by 2 from 0 to T by 2. This is the output. Okay, so for the negative half cycle, like this one, for the negative half cycle, the current will flow in this direction, and the diode will be in the on state. So this is the final figure. It is showing 0 to T by 2 is 0, whereas T by 2 to T by 2 to T is the original signal, in which the lower half is shown here. So if I plot it here, then it will be like this one. Okay, it's not very neat, but at least we are getting what we need to know here. So this is V of I minus V of I. So this is minus T by 2. We're getting the values here. Okay, so what is the average DC value? The average DC value for the A is VDC is equal to minus 0.318 Vm. This is equivalent of minus 6.36 volts. Okay. For the B part, repeat part if the ideal diode is replaced by a silicon diode. For a silicon diode, the output has the appearance of figure 2.51. Just see the difference here. Let me find in color red. So what we discussed lately, that these are two patches with the value of 0 here. So the average DC value is approximately equal to minus 0.318 Vm minus 0.78 is the silicon diode. So it is equal to minus 0.318 into 19.3, 20 minus 0.7, this is equivalent of 6.14 volts. The output value will be like this, because we need input potential to reach a threshold value. We need to wait for the input signal to reach the threshold value so that the peak will in a voltage value will start rising, like up to here. So up to here. So in case of input signal, this one up to here, we need this value to reach the threshold value. Like this is minus 0. This is 0.1, diode will be off. 0.2 diode will be off. 0.3 diode will be off. When it reach here, it is 0.8. So diode will be in the on state, and we'll be getting a output value of like this one. Okay, coming to the third one. Repeat parts A and B if the VM is increased to 200 volts and compare solution using equation 2.7 and 2.8. So equation 2.7 is the resulting drop in the DC level is equal to 0.22 volt, or about 3.5%. This is for the part B. Now coming to part C, VDC is equal to minus 0.318 due to this one, this lower lobe. 200 is equal to minus 63.6. This is 200 because we are using the ideal diode. But in case of silicon diode, it will be VM minus VK is equal to minus 0.318 into 199.3 volts is equal to minus 63.38 volts. Okay. So what is the peak inverse voltage? Peak inverse voltage is the rating of a diode that the rating of the diode must equal or exceed the peak value of the applied potential. This is the relation. PIV rating is greater than or equal to VM. Diode must be the rating of a diode must be greater than or equal to the input potential, which is V of M. Otherwise, it will not work. Okay, hopefully you are getting a clear idea about the half wave rectification. In the coming lecture, we will be discussing the full wave rectifier and with an application of center tap transformer.